Hello everyone, we are Group 12 and today we present our project on content based image retrieval or CBIR. Our team members are Neha, Pooja, Abhishek, and me, Nikita. We'll walk you through the motivation, the methods we used, our results, both strengths and weaknesses, and finally, the improvements we see for the future. Now let's start with the basics. What is CBIR? CBIR is a way to search and organize images based on their actual content, things like color, texture, or shape, rather than just relying on the file name or tags. Why does this matter? Well, image collections online are exploding in size. Think about all the product photos in e commerce or the millions of scans in healthcare databases. Most of these don't come with detailed, accurate tags. Adding them manually is slow and subjective. What CBIR does instead is work directly on the pixels. So, if you want to find shoes that look similar in a photo or medical scans with similar patterns, you don't need text. The system learns from the image itself. Applications of CBIR are everywhere. In healthcare, CBIR can assist radiologists by pulling up similar X rays or MRIs. In retail, is the tech behind find visually similar products. In security, it's used for facial recognition and surveillance. And in digital archive, it helps organize large photo collections or even artworks. The big challenge is what's called the semantic gap, the difference between low level pixels data, that is the something like colors and textures, and high level meaning objects, scenes, or concepts. That's the tension CBIR research is always trying to solve. Researchers have approached CBIR from two perspectives. On one hand, Schaefer in 2011 focused on low level features, color histograms, text descriptors like LBP, and shape features. These are efficient and easy to compute. Color histograms, for example, are fast, rotation and scale invariant, but they ignore structure. On the other hand, Data ETAL at 2008 emphasized the semantic gap. They showed that while low level features are useful, they don't match human perception perfectly. Their survey pointed towards combining features and eventually machine learning to bridge that gap. So, the story so far is low level features give us a strong baseline, but to really match human intuition, we need higher level approaches. Our project sits squarely in the middle of the story. We build a baseline using histogram to demonstrate the process and its limitations. Here's how our method works. Step 1 is feature representation. Every image is converted from RGB into a quantized space, just 2 bits per channel. That gives us 4 levels per channel or 64 possible colors in total. Each image is represented by a 64-dimensional histogram vector. In MATLAB, we use RGB26CC to quantize the RGB space and get his counts to generate the histogram. So, instead of working with raw pixel arrays, we compress every image into a consistent 64 length vector. This keeps computation efficient but still captures dominant color information. Sorry. Okay. Next comes similarity calculation. We take the histogram of the query image and compare it to every histogram in the database. The distance metric we use is Euclidean distance. This is a baseline choice, simple, interpretable, and widely used. We then sort the distances in ascending order. That's done with MATLAB sort rows. To avoid trivial results, we remove the query image itself from the ranked list. Finally, the distances and rankings are saved as distances.mat and rankedistances.mat so the results are reproducible. This modularity means we can later plug in better metrics or features without rewriting the whole pipeline. So now, how does it perform? Let's start with the positives. The system is very strong at color matching. If the query image has a dominant color, the top results tend to share that palette. It also handles background consistency well. Blue skies, oceans, or vegetation come out grouped together naturally because the histograms reflect those dominant areas. And it's fast. Retrieval happens in under a second, which is great for interactive use. For example, if a query with a red sports car, the system brings back other red cars or red colored objects. A blue sky beach scene pulls in similar coastal landscapes. That shows histograms are effective when color is a main distinguishing feature. But there are obvious weaknesses for it. Um, like color collisions. Different objects with the same palette look identical to the system. For example, a red car query may also retrieve red flowers or red stop signs. Light sensitivity. The same object under different lighting conditions may not match at all. No spatial or structural awarenesses. Two patches of green could be confused for a forest even if they are just grass in one corner of the image. Some of the examples, like querying a zebra, brings back random black and white patterns like striped shirts or buildings. A sunset might just return anything red or orange, even if it's not a landscape. These illustrate why histogram only retrieval can solve semantic level tasks. This is our output where query101.jpg is our input and the remaining images are our outputs, where you can see like in the beginning the outputs are very relatable, but later on it's not. Now, to measure performance, we use standard information retrieval metrics, precision, recall, and F1 score. Precision is the fraction of retrieved images that are relevant. Recall is the fraction of relevant images captured within top K. And F1 score is the harmonic mean of precision and recall. These are some of our sample results, like precision at 5 was 0.82, then precision at 10 was 0.76, recall at 5 was 0.63, recall at 10 was 0.71, and then F1 at 10 was 0.73. These are just sample. So we can say that the performance is solid at small k, but weakens as more images are retrieved. That's consistent with what we saw qualitatively. Strong when colors dominate, weaker when semantics matter. Here's what we have learned. We successfully built a baseline CBIR system using color histogram and Euclidean distance. It's fast, easy to interpret, effective for color driven queries, but it's also limited. It ignores spatial layout, it's sensitive to lighting changes, it can't capture semantics like objects or context. For future work, we'd look into better metrics like Earth movers distance, spatially aware features like coherence vectors, texture descriptors like local binary patterns, or shape features like edges or moments. And ultimately, CNN based features which bring in semantic power from deep learning. These are some of the future improvements. So, I can say that this project is not the final answer. It's a clear first step, a baseline that shows what's possible and what's missing. These are some of the references we used. Swain and Ballard on color indexing, Smulders on the state of CBIR, data ETAL on modern trends and semantic gaps, and Schaefer on practical introductions. These gave us both the theoretical foundation and the practical direction for our project. Now let's see our demo. Okay, uh, here in our demo, I'll first pick a query image, extract a 64-bin color histogram, compute Euclidean distances to all images in our database, and show how we read the results for a ranking. First, here we resolve project folders and sanity check that data or input exists. We also ensure data meta is present for our outputs. Then we load db.mat, which stores one 64 dimension histogram per image. The assert guarantees the database is n into 64. Now I'll choose a query image with UI get file. If it's grayscale, we promote it to 3 channels. And if it's anything other than 1 or 3 channels, we stop. This guarantees the next step sees a valid RGB image. In this, 2 functions do the heavy lifting. That's RGB26cc and get his counts. RGB26cc quantizes RGB down to 2 bits per channel, which is 4 levels each, giving 64 possible colors. And then get his counts. Um, it builds the 64-bin histogram for the query. This matches exactly how we build db.mat, so comparisons are apple to apple. Everything's right. Next, here we compute the Euclidean distance to every image, which are vectorized and no loops. And dbq is this broadcasts the query against all rows and gives the distances. And this gives the distances. Now, using the this is how we display our output. Let's run the code and see what we get. Here it asks us to choose an image. I choose image 101. Here's the output. Here, the first white tile shows the query with its file name. The name is on top. The next tiles show the top 20 results with rank and file name and distance printed in the tile. The distance is also printed in the tile. It's a quick visual check of retrieval quality. So this is exactly how it's running. So that's the demo flow, guys. Mm, the demo flow is nothing but BigQuery, extract 64-bin histogram, vectorize Euclidean distances, save artifacts, and inspect. That's the basic flow. We'll see great matches when color dominates, and we'll also notice failures when different objects share palettes or lighting shifts. Exactly the trade-offs we discussed. That's it for today. Thank you so much for listening.